Okay, welcome back. I hope the organic chem midterm went okay for you. But now you can put that behind you and focus on the biochem midterm and maybe stats. So just to get them on the recording, I'm just going to flash through these slides. I was asked to put this is actually today. If you want to work out in the outdoors when it's raining, you can pay $5 for that. It's a good cause. And then this one, just so it's on the recording, you can go here to apply if you're interested in this. Okay. Midterm, Saturday, 2 to 5. So it's a 3-hour midterm. It's on topics 1 to 13, as you know. 90 multiple choice questions, and this approximates the number of lectures that each Dr. Boff and I gave on the topics. Once again, you'll have a question and 5 answers. And one of those hopefully will be right. And so that's going to be the test. So Dr. Dempsey, if he hasn't already, he is soon will be releasing your room assignments on Postum, same way I distributed the assignment teams, right? So please check that out when it's available. It may be up there now, it may not be, but if it's not, it will be soon. You please, I can't stress this enough, right in the room that we're assigning you, because Dr. Dempsey's got it all planned out. There's many students and we have lots of rooms. And if people start going to rooms they haven't been assigned to, then we could end up with too many students in a room, not enough exams, and it creates a lot of confusion. And that may cost you time to sort when we're trying to sort that out. So you are expected to go to the right room, and students who do not or are found to be not in the right room will be made to go to the right room, but we're not going to give you any extra time. I mean, it's your responsibility to get to the right place. If you're writing with accommodated exams, those students who have accommodations, write wherever they tell you to write, okay? So regardless if Dr. Dempsey assigns you to a room, you should write with accommodated exams as they direct you, okay? Just in case you're looking for help, tomorrow we have office hours as usual, and Dr. Bofus are over Zoom. Mine are in my office, but if you want to meet me over Zoom, send me an email and I will send you a link for the Zoom call. But I won't open that unless people ask for it. And then we have these sessions, which I announced, well, twice, once without the date and once with the dates. So Wednesday, a couple of TAs, Dan and Owen, are working on some just summary stuff to go over some of the key concepts or things that students tend to struggle with. And that's on Wednesday, 4:30 to 6:30 in the Arts and Humanities building, okay? And then Dr. Bofa and I will be in Health Science Building 40 on Thursday afternoon to take questions. And so we're not preparing anything for our session. We've already presented the material the way we know how to. But we'll be accepting questions. And of course, the Biochem Forum is also a great place to get your questions answered. I've been answering questions there as they come up. Okay, notice that Health Sciences Building is different from Health Sciences Addition. Okay, those are HSA and HSB are 2 different buildings. So this is the Labatt Health Sciences Building down sort of across from, well, by the new FIMS and nursing building. Okay, all right. Now, just some advice. Again, I stress it, go to the right room. You got to bring your student card. You know, you need ID or you won't be able to write the exam. You need to bring a pencil. Don't use pen on the Scantrons. It won't pick them up. So you have to, we're not providing pencils, okay? Or erasers, if you're the type of person who needs an eraser from time to time. So bring your own. You're not supposed to have bags and things at your desk when you're writing, so you will be asked to put them, if you bring stuff in, you'll be asked to put it at the side or the front of the room. Please follow the proctor's directions in this regard, and also with seating. Electronic devices, you sort of goes without saying, you're not allowed to have your phones on you when you're writing an exam. If you're caught with your phone, you will get 0 on the exam. That's just the rule. So please, I don't want to have to do that. So either leave it in your bag, leave it in your jag, leave it at home. I mean, you can probably maybe do without your cell phone for a few hours. I don't know. But if you're worried about it going missing or wandering, you could just leave it at home. Otherwise, leave it in your bag. Don't have it on your person. And likewise, no calculators. This has been discussed on the forum a bit. Any calculations you have to do should be straightforward arithmetic. Okay, and we're expecting students at your level to be able to do that. Read questions carefully. It sort of goes without saying, but sometimes students get anxious and they get, rushing and they're worried and they skip over the question. So often it's impossible to write questions where if you misread a word that you're not going to get the wrong idea, right? So it's not that it's a trick question or anything. It's just if you miss the not or miss the always or some other word, you're probably going to misinterpret the question. So just slow yourself down and read the questions carefully. We try to word them in as straightforward a way as possible. So if you can think of a convoluted way to read the question or a straightforward way, go with the straightforward way. Okay, I'm not trying to write deliberately like tricky questions that are going to be confusing to you. If you get the question wrong, I want it to be because you didn't understand the material or the concept, not because you didn't understand the question. Okay, so I do my best to write them clearly. Just read them carefully and take your time. And record your section on the Scantron sheet. If you're here right now, I'm expecting you to be in section 2. And that helps us identify students later. And one thing you should not do is panic, regardless of what is going on, the exam going on your mind. Try to keep your blood pressure down. I mean, it doesn't do you any good to get your mind racing. Oh no, I'm going to fail this exam. Oh no, I'm going to have to drop out. I'm not going to get into medical school, whatever, don't think about those things. Okay. If you read a question, I remember going my first year calculus exam and it was a question worth a significant proportion of the exam. And I flipped the page and I'm like, I have no idea how to do this question. I remember this very vividly sitting in that exam. And I was just like, oh, well, and I moved on to the next page, right? So that if you get a question like, wow, I don't even remember them talking about this, just move on to the next question and, take a guess later, right? But don't let it just put it out of your mind for the moment. Get the easy ones first. If you find any easy ones, do them first, I would say. But, and eat also, please eat. We've had sometimes students get in trouble because they've, not eaten breakfast or whatever, and they're low blood sugar and you need blood sugar. Okay. So, and we've had students, going through, almost like a seizure thing. We give them a banana and they're fine. So just, just please, take care of yourself. And I don't know about eating and drinking during the exam yet. I'm meeting after this class where I'm hoping to hear something about that. But for now, I've been told you're not allowed to eat or drink in the exam. That's what I've been told. So that's what we're going with. Okay. If you have other questions about the exam, post them to the forum and everyone will see the answer. Okay. So we're going to dive into topic 12 now. I probably won't get it done after that big preamble, but we'll get pretty close. This comic here shows Calvin leaving a birthday party and had a nice interaction with Susie. She gave him some cake and ice cream, and to bring it home to his mom, he decided to just stick it in his pocket. And if you know the pockets of young boys, it's probably not the best place to put anything you want to eat. And so this, if you want something to be useful, you got to package it in an appropriate way. And that's where hopefully I'll remind you of that when we get to that point in topic 12. Okay, so here we are, we're almost there, and we'll be done certainly by Wednesday. I know it's probably cutting a little close for some of you about, covering the material before the midterm, but this is actually standard practice in this course. So we're not treating you differently than other years. We'll definitely get most of 12 done, and 13 is mostly a review to tie things together. Okay, but now we got a little story about Sorab. Last time we left Sorab, he made dinner for his female friend who's running the marathon. And so he did that. That all went great. Her marathon went really well. And he went and sort of watched her on the finish line and congratulated her. And he thought, wow, that's really impressive. I need to get in shape, is what he thought. So he starts running. He does a little running, and then he does these push-ups, and you can see he's left the ground there. That's pretty good. And he does some kickboxing. This is what Sorab's into. So he's working out, trying to get in shape to maybe impress this young lady that he's developing a relationship with. But let's suppose that he really goes for it and he kickboxes all day until he exhausts his supply of glycogen. And so the question is, Where do you think his muscles will obtain energy if he keeps on working out? Okay, 10 more seconds. Okay, so half the people thought both glucose and fatty acids made in these ways. And then, yeah, so we have some other options. So that is actually correct. Okay, so when glycogen stores run out, the liver, well, first of all, when blood glucose starts to fall, the liver will mobilize glucose from glycogen, right? And put that in the bloodstream. But there's only a finite amount of glycogen. So when that glycogen runs out, if the energy demand is still there, then the liver will do gluconeogenesis. That glucose gets produced and put into the bloodstream for the benefit really of the brain, because the brain is focused on, it really likes getting glucose as a source of energy. But muscle cells will use that too. Muscles, they're not above, stealing glucose that's meant for other body parts. So muscle will use that glucose, and muscle also can use fatty acids that are released from adipocytes, which is our other major source of energy storage, right? Those triacylglycerols get put into adipocytes. So muscle is opportunistic and will use both of these types of energy. Okay, so then we'll talk about the lipid part of it in topic 12 here. By the end of this topic, you should know all what happens to acetyl-CoA. You should complete what happens in the mitochondrion. We'll talk about fatty acid synthesis and degradation. We'll talk about these things, ketone bodies, and we'll talk about regulation as we do. So here's our master diagram. We've talked about most of it by this point. And in this topic, we are focusing on these processes here, the ketone body part, and also synthesis and degradation of fatty acids and triacylglycerols. Okay, so we're going to start off talking about releasing triacylglycerols from fatty acid storage. So under low glucose conditions, you're working out, you're really strenuous, and your body is looking for energy. One thing it will do, it'll turn to the stored triacylglycerols, break those down to fatty acids, and we can break those down to acetyl-CoA, and in this process, get some NADH and QH2. And acetyl-CoA, of course, itself can feed into the citric acid cycle to give us even more ATP, right? And this process where you take fatty acids and break them down into acetyl-CoA is known as beta oxidation of fatty acids. So when you see that phrase, that beta oxidation, that means taking fatty acids, converting them to acetyl-CoA, and it's an oxidative process. You're removing electrons. Those electrons go on to NADH and QH2. All right. But first, we need to get the fatty acids, right? So we need to break the triacylglycerols down into fatty acids. So in topic 6, I introduced this molecule, triacylglycerols, and it's got 3 fatty acids joined to a glycerol backbone. And so there's an enzyme called lipase that will reverse the process of adding the fatty acids to the glycerol. It'll break them off. Okay, now the fatty acids are free and can be used. We can break them down to make acetyl-CoA, which is good for making ATP. And so that's just the process there. What happens to these fatty acids, of course, get released into the bloodstream. Different tissues take them up, but notably not the brain. Now, this is one reason why the liver needs to worry about the brain, because the brain does not take up fatty acids and use them as a source of energy. So the liver has to sort of make allowance for that. That's one reason it tries to stick to glucose and makes glucose and gluconeogenesis, for example, because even when there's lots of fatty acids in the brain, they won't cross the so-called blood-brain barrier. So, but other tissues like muscle and liver will take up the fatty acids and oxidize them to make acetyl-CoA. And then furthermore, the glycerol gets released into the bloodstream. The liver will take that up, and that is a substrate for gluconeogenesis. So this is handy because this happens under low blood glucose conditions, right? So when glycerol is released from this, the triacylglycerols, you can use it to make glucose. And there'll always be demand for glucose in the body. Okay, so that's what happens here, and this is the whole point, and that should more or less make sense. And so I got this little picture where I'm showing these different types of tissue. The triacylglycerols are stored in the adipocyte or fat cells, right? And that gets broken down into fatty acids and glycerol by lipase, and those get released into the bloodstream. And then they have different fates. If we look at the glycerol, it gets taken up by the liver, it does gluconeogenesis to make it into glucose, and then it puts it back out into the bloodstream, and the brain and other tissues will gladly take up that glucose and use it to make ATP, okay? But the fatty acids are not picked up by the brain, but they will be picked up by liver and muscle to make acetyl-CoA, and that goes into the citric acid cycle and is used to make ATP through oxidative phosphorylation, as I covered in topics 10 and 11. And so this then is under low glucose conditions, this is where the liver gets its ATP or gets its energy from, right? So the liver itself, under low glucose conditions, is not going to consume glucose. Okay, it's going to save that for the brain and the rest of the body, and it's going to get its energy from fatty acids. But there's lots of energy in fatty acids, so that's going to be enough for the liver to use. And the muscle, as I said, will also pick up fatty acids. Muscle, it will look for any source of energy it can get, and it'll use it. Okay. And so that's the basic, just to give you the big picture of what's happening, because I'm talking about different tissue types. So I sort of created this diagram to try to help you with that. So here's a question. This enzyme lipase is sensitive to hormones, and in particular, it's sensitive to insulin and glucagon. And at this point in the course, I'm really hoping you can answer this question about how insulin and glucagon are going to regulate this enzyme, hormone-sensitive lipase. Okay, I'll give you maybe 10 more seconds now. All right. Okay, so the most popular answer was A, that insulin is going to inhibit this enzyme and glucagon is going to activate it. And then the next most popular was B, which is sort of the reverse of that. So I like that people are recognizing that insulin and glucagon are going to have opposite effects. Okay, so that's when you're looking at this, it's, insulin and glucagon represent two different states, right? When insulin is present, that's when you have high blood glucose. And when glucagon is present, that's when you have low blood glucose. So that is, it stands to reason that those two, under those two circumstances, you're going to regulate this enzyme oppositely. And so the majority got it correct. When there's high blood glucose, there's no real need for you to reach into your fatty acid storage to provide energy because there's lots of glucose around. And glucose is the easiest thing to use. And conversely, when glucagon is high, there's low blood glucose. So that's a good time. That's to release some energy from fatty acid storage. So A is the correct answer here. And we'll talk more about regulation at the very end of the topic. But for now, we're going to now think about what happens to those fatty acids once they get into the cell. How does the cell then break them down to use them to get ATP? And the first thing that needs to be done is to transport the fatty acids into the matrix, because the breakdown of fatty acids by beta oxidation occurs in the matrix, same place you do citric acid cycle, right? And so it just turns out that to transport them into the matrix, we need to activate them first. Activate them by adding the fatty acyl chain to coenzyme A. So here's our friend coenzyme A. Remember, we talked about acetyl coenzyme A. That's a 2-carbon fatty acid joined to CoA. Here we have longer chain fatty acids that get joined to coenzyme A. And to do that, we need to use ATP. So this is one of those reactions where we need not just going ATP to ADP, but we actually take the 2 terminal phosphates off to give you pyrophosphate, and then those are cleaved apart to get 2 phosphates, and you end up getting an AMP, adenosine monophosphate, out, and this shows you the intermediate that happens during the enzymatic process. Because the basic idea is that adding the CoA group sort of activates them. This is now even in a high energy state just with the CoA on it, and so you need a little bit of extra push, extra energy to get that coenzyme A on there. Okay, so there's an example of a reaction that takes more energy. And then that coenzyme A bound acyl group, or the acyl CoA, that's what gets moved into the matrix. There are transporter proteins that will move fatty acids from the cytosol into the matrix. Okay, so once in the matrix, what happens is we get a series of reactions that occurs repeatedly on that fatty acyl chain to break off small bits of it at a time. You basically take off 2 carbons at a time and you put them onto coenzyme A to give you acetyl CoA. And then the cycle repeats itself, because you start out with a long acyl CoA, like let's suppose it's 16 carbons to start, right? That's a typical fatty acid size. It's got 16 carbons. In the first round, you take off 2 of those carbons and you get an acetyl CoA, and you end up with a 14 carbon acyl CoA. And then you do the things again, and you take off another acetyl CoA and you get a 12 carbon acyl CoA, and so on until the last step you got a 4 carbon acyl CoA, and basically you split it in half and you get 2 acetyl CoA groups. Okay, and during these reactions, each time you do one of this sort of pseudo cycle of reactions, it's an oxidative process, because if you imagine the 16 carbon saturated fatty acid, it's got a carboxylic acid group on one end, and the rest of it's all hydrocarbon chain. But what we're doing is actually adding a bunch of oxygen to the carbons, right? Because you end up with a bunch of acetyl groups, each one of which has an oxygen. It's an oxidative process, and the electrons end up going, you put 2 onto Q to make QH2, and you put 2 onto NAD+ to make NADH. Okay, so you're taking 4 electrons out each time you produce an acetyl CoA. And you get a bunch of acetyl CoA in the end, and a bunch of NADH and a bunch of QH2. So, and then the diagram in the book shows you the reactions. You're not responsible for the individual reactions as usual. Just get the overall process. And in fact, I'm not even going to worry about stoichiometry so much here. Just know that you take a long chain fatty acid, you make a bunch of acetyl CoA with it. And so if you start out with 2 N carbons, where N is say 8, if you started out with N equal 8, you'd end up 16 carbons at the beginning, you end up getting 8 2-carbon units at the end. So you'd end up with 8 acetyl CoA units. And then you end up with N-1 QH2 and NADH. Now, again, I'm not so concerned about the stoichiometry, but often this confuses people. Why don't you get N-QH2 and N-NADH? Well, just remember in that last step, you take a 4-carbon unit and split it in 2. So basically, if we started out with 4 carbons, a really short acyl CoA, you'd only need 1 flip around the cycle to make it into 2 acetyl CoA, right? So if we started out with N equals 2, you'd only need 1 turn through the cycle. And if N was basically if you had 6 carbons at the start, you do the reactions twice to get 3 acetyl-CoA, but only 2 QH2 and 2 NADH. Okay, so if that still doesn't make sense to you, just think about it. And you can always post to the forum and I'll explain it in writing there. Okay, so but the point is you get out of this acetyl-CoA, which can go into the citric acid cycle, which we already saw is good for making even more NADH and QH2 and GTP. And those NADH and QH2 are good for making ATP by going through the electron transport chain and ATP synthesis, so oxidative phosphorylation. Okay, so the whole point of beta oxidation is to give us these molecules that can be further metabolized to make ATP. You don't make any ATP directly from beta oxidation, you'll notice. No ATP is produced in this process. But you can make a whole bunch of ATP by further metabolizing these molecules. The other thing that happens to acetyl-CoA is called foreshadowing in English class, is they get converted to ketone bodies, which I'll talk about in a few slides. So in particular in the liver cell, the liver will use some of the acetyl-CoA for its own energy needs. But again, because liver is so selfless, it's always thinking about what's going on elsewhere, and it's going to convert some of that acetyl-CoA to ketone bodies, which are used by other tissues. Okay, so that's the process of beta oxidation. So get the point of it. It's just to allow us to make ATP. So that, if we go back to the master diagram again, and I'm going to back to a few times just to make sure everyone's oriented. I mean, I talked about breaking triacylglycerols to fatty acids and fatty acids to acetyl-CoA. And now I'm going to talk about ketone bodies. Okay. And what are ketone bodies? Really, there's 3 compounds that are referred to as ketone bodies. And the 3 structures are shown here. You can see they're pretty small. They're 3 or 4 carbons. And they are called ketone bodies. So it stands to reason they have ketone groups. And you can see acetone has a ketone group and acetoacetate has a ketone group. And this one does not have a ketone group. So that is just acetoacetate that has been reduced down to the alcohol version. This is still often, or a lot of people, or most people, I'm going to lump it in, include it in the ketone bodies because it's so similar to acetoacetate. See, the structures are very similar. Okay, and so what these are, they're just small carbon molecules that can go into the bloodstream, and in particular acetone, it's not very polar and can readily cross membranes. And so it can get into places that other things can't. And in particular, these molecules will cross the blood-brain barrier. Okay, and so that is the main reason that the liver bothers to do this, to take acetyl-CoA and make them into ketone bodies. It's because under low glucose conditions, the brain is hurting for energy, and it does not take up fatty acids. So this is a way of repackaging the fatty acids. Think Calvin bringing cake and ice cream home to his mom. It would be better if he put that in some sort of a container, like a Tupperware container or something, before he stuck it in his pocket. So this is sort of like wrapping the fatty acids, the acetyl groups, into something that the brain will accept as a form of energy. Okay, just like his mom would accept some clean cake as opposed to stuff that's been in his pocket. So this is the whole point then. So this allows the brain to use the energy obtained from fatty acids. It's sort of repackaging the fatty acids in a way that the brain will accept. Okay, so then, and this particular happens during the extended fast. And again, I'll get to this in topic 13. We'll go through the stages of fasting, but this is a more complicated process than just releasing glucose or making glucose. So this is a bit of a longer term thing. Once you're really low on glucose for a while, this will get upregulated. So what happens, the liver takes up the fatty acids and it converts them to acetyl-CoA, and it'll use a lot of that for its own use, but then it'll also make some of it into ketone bodies. And those get released into the bloodstream, and the brain will pick those up. And the brain converts them back into acetyl-CoA, which then it can feed into the citric acid cycle. Okay. But you can imagine that this process then, to convert the ketone bodies to acetyl-CoA and to make them in the first place, this requires upregulation of certain enzymes that are not normally around. So this is a bit, it takes a little while. Basically, the kernel of the idea is it takes a while for the fatty acid metabolism to fully get into full activity, for flux through these pathways to be really high. So this is during an extended fast, or when you are under some sort of chronic low glucose conditions, the fatty acid metabolism tends to get raised. Now, most of us in North America aren't in those circumstances, right? We just naturally, we'll talk about me, I like to sit and eat. And so under those conditions, I'm getting lots of glucose, and my body doesn't necessarily have to dip into its fat reserves too much, right? So this is one advantage of exercise. You know, it sort of keeps your metabolism working, and it can keep these pathways sort of going at some basal level, more so than a person who's not exercising. All right. But again, I'll wrap this up again in topic 13, so we'll talk about it again. But the basic point now is the ketone bodies are how the brain gets energy from fatty acid storage. Okay. And the liver has to do this because the brain does not take up fatty acids directly. Okay. Okay. So that's just a little bit of ketone bodies are pretty important if you're under fasting or starvation conditions. But there's not much else to say. I mean, again, I could make it more complicated, but I'm not. So now we've talked about breaking down the fatty acids, and now we're going to switch gears and talk about the reverse process, right, of synthesizing fatty acids. And that's going in this direction, acetyl-CoA, going to fatty acids. So this would then be under high glucose conditions. So now we'll reorient ourselves to stop thinking about low glucose and start thinking about high. After you eat a meal, you're going to get lots of sugar there, lots of glucose. There's probably lots of fat, or some anyway. And so the fat might be there, but then if you're taking glucose and you're breaking it down through glycolysis, and it goes into acetyl-CoA, some of that, of course, is going to be used in the citric acid cycle. But if there's lots of it around, you want to store some of it away for when you need it, right? And that's the fatty acids. You make them to synthesize them, and those will give you energy later under such a time when you don't have a lot of glucose around. So, and it gets awkward again because you got to move this acetyl-CoA around. I talked about moving the fatty acids into the matrix because, and I should have emphasized this point, right? When you break down the fatty acids in beta oxidation, you're making NADH. And it's really handy for that to be in the matrix because then that can go right onto complex 1, right? So that's why the fatty acid beta oxidation happens in the matrix, because then it's very convenient for it to give electrons to the electron transport chain. But it turns out when we synthesize fatty acids, we do that in the cytosol. It's sort of a way of separating the two processes, okay? So that, you know, it just helps regulate them. But acetyl-CoA, you know, from pyruvate, that happens in the matrix. So now you got to move it out into the cytosol. That's where the fatty acid synthesis happens. And so that, produced in the matrix, this happens in the cytosol, right? And that's produced right from pyruvate, which is made from glucose. We're talking about sugar breakdown here. So we need some way to get it across. And just like when I was talking about moving NADH from the electrons from NADH from the cytosol to the matrix, there is a bit of a cycle or a bit of a pathway that is used to move the acetyl groups. We're not going to cover the details of it. If you're really curious, you can piece it together from these two figures in your textbook, but even they don't give the whole story. But what I want you to know is what's in these boxes here. The basic point is you take acetyl-CoA in the matrix and we move it into the cytosol. We end up with acetyl-CoA in the cytosol. This costs us some energy, 2 ATP in fact. So that's a little bit costly. And then it's interesting because there's redox chemistry happening here, and it gets, you know, one redox reaction happens and sort of gets reversed later on. But it's interesting because this is a case where in one direction we have used NADH, so we take electrons off of NADH, but then when we put them back on an NADPH. Okay, and this is it's a bit unusual to have one sort of pathway or cycle that uses these two different energy or electron carriers. But in this case, it makes sense. Remember, we're under high glucose conditions, so we're probably making a lot of NADH. And we want to do a biosynthetic process here, take acetyl-CoA and make fatty acids. And you'll see from my little diagram, NADPH is the electron donor when we contribute electrons to make the fatty acids. So what this does, this helps you get enough supply of NADPH to allow fatty acid synthesis to happen. It's actually pretty clever of evolution or the cell or whatever, God or whatever you want to think. It's pretty clever that this is the way it works, right? That when under conditions we have lots of NADH, this is a way we can transfer some of those electrons from NADH to NADPH, so that it's in a process that is setting up this movement of acetyl-CoA into the cytosol, setting up fatty acid synthesis, and so we make NADPH, which is a substrate for the thing that's about to happen. Okay, so it's pretty clever. So I guess I'd expect you to know for the I do expect you to know for the test on Saturday that when you move acetyl-CoA from the matrix to the cytosol, it costs us 2 ATP, but we also are able to transfer electrons onto NADPH. And then we get this synthesis process. And if you look at the chemistry of this, it's basically the reverse of beta oxidation. It's not exactly, but that's the same idea. And so you're taking 2 carbon units and you're joining them together. And you go around the cycle and you join 2 and 2 together to make 4, and then you take another 2 and you add that to the 4 to get 6, and then you take that 6 and you add another 2 to get 8, and so you're building it up in 2 carbon units, just the same way that beta oxidation broke them down in 2 carbon units. Okay, but this does cost you some ATP. Every time you go around and add another 2 carbon units, it costs you ATP. And you have to put in 4 electrons. Just remember when we did the reverse process, we got out an NADH and a QH2, that's 4 electrons. In the reverse process, we have to put back 4 electrons. Okay, and those 4 electrons come from NADPH, as I just said. You don't get quite enough NADPH out of that transport process to completely meet the need here. So you still will need NADPH from the pentose phosphate pathway to do this. But the transport of acetyl-CoA into the matrix helps. And so this reaction continues and continues, and you make a long fatty acyl chain. And sort of the default or the standard product that you make from this is palmitate, which is the 16 carbon saturated fatty acid. You're not responsible for memorizing the names of fatty acids, so I expect you to know that palmitate is a 16 carbon saturated fatty acid, but that's what it's called. But we can make longer ones or shorter ones depending on what our needs are. And there's another step if you want to add a double bond. We're not going to talk about that. Just be aware that you can add double bonds or a double bond. Okay, mammals basically can add a single double bond if we want. Okay. So then if we look at the net reaction for this, if you're making the saturated 16 carbon fatty acid, you need 8 acetyl-CoAs to do this, right? 8 2 carbon units come together to make a 16 carbon fatty acid. The CoAs, the palmitate then can be used to make triacylglycerol. It can be added to glycerol. You can store it away as fatty acid storage, or you can use it to synthesize membrane lipids, right? And this is a good thing to do from time to time. You need to replenish the lipids because there's lipid turnover and things get messed up. So you got to replenish and keep making your lipids. And this is under high glucose conditions. So it's a good time to be doing biosynthetic processes to build things up because you have energy to spare. And in this process, you need to get a source of electrons, and those come from NADPH. And again, it's 2 NADPH, right, for every 2 carbons that are added. But in the first cycle, you're taking 2 and 2 to make 4. So to make a 4 carbon thing, you only need 2 NADPH. anyway, it works out this way, that the stoichiometry is to go 7 times through the cycle, you'd make a 16 carbon thing, and you need 7 times 2 NADPH. But don't worry so much about the stoichiometry. Just be aware that this process consumes NADPH. Those electrons go on to the carbons. And then it also consumes some ATP, because you need to put energy in generally to do biosynthetic processes. And as I said, you can make longer or shorter, and that will affect the stoichiometry. You can also introduce a double bond. And talking about double bonds, that reminds me of something I forgot to mention, and I'm sorry about this, and the beta oxidation, but it is a point I just wanted to make. And I'm wondering, go back. Where are we going? Sorry to do this to you. Oh, come on. Okay, so sorry to do this, but I feel I should come back and say it, because I meant to say it before. Okay, so I talked about beta oxidation of an even chain fatty acid. But I didn't talk anything about what about an odd chain fatty acid. You might get to think, oh, well, maybe we don't break down odd chain fatty acids, but we do. So our system can handle, 17 carbon fatty acids when we intake them. It just gives a slightly different product, because in the last cycle, you're left with a 3 carbon unit. And basically that gets converted to a 4 carbon unit, which goes into the citric acid cycle as succinyl-CoA. Okay, so but don't worry about the details. The main point is we can handle odd chain carbon fatty acids, and we can handle unsaturated fatty acids. So here I'm talking about a saturated acyl-CoA. It's the same type of process would happen if we have an unsaturated fatty acid. It just turns out that one of the reactions in this process involves creating a double bond, and that's an oxidation reaction, and you get electrons out, and in that process you make a QH2. So during one of these reactions, this reaction here that makes a QH2, it's formation of a double bond. But if you've got an unsaturated fatty acid, you have a double bond there already. Okay, so it allows the process to skip this step. So you end up making less QH2 if you have a saturated fatty acid. Okay, so that's just a little point that I wanted to make, just so you're aware that our bodies can handle things other than saturated even chain carbon fatty acids. So if it's an unsaturated fatty acid, you're going to get less QH2. So that's just a little point. But I thought it was worth mentioning. Okay, there's ketone bodies. That's where it was. Okay. So sorry about that. I hate going out of order like that, but I thought I should mention. Okay, so now we're going, let's finish off with Sora. We got 7 minutes left. Okay. So I've gone over fatty acid breakdown, ketone bodies, and fatty acid synthesis. All right, so that's the basic stuff, and it probably felt a little fast, but we're condensing it because again, we're not going into all the details of the reaction. So now Sorab, he started working out. He's feeling good. He's sort of seeing this young woman, and he's really liking her, and things are going great. But every now and then you go out with your friends, and maybe it's not with your significant other. So, Sorab and his friends decide to have, sort of a guy's night out, and they're going to go to the Palisade and just hang out and have fun, because his girlfriend's busy, and that's fine. He's going to go out. So he gets with his buddies, and they go and they're having a good time, and they get there, and as soon as he walks in, who does he see across the room? But his lady friend. Right? And she's with some other guy. Yes, it's true. And and they're playing pool, and it looks like they seem to be, like there's nothing going on, right? But they're together. They're clearly together, clearly having fun. And Sora takes one look at that and he says, guys, I just can't. And he's out of there, like, because that's really discouraging, right? So he turns off his cell phone. He doesn't want to talk to anybody. because he's just heartbroken by this. And under such circumstances, of course, what do? You turn to your good friend, ice cream, okay? So here's Saurabh, he's feeling sad, and he's working on this thing, but you know, sometimes he just can't help himself. He's very sad. So let's leave him in his misery for a moment and consider what's happening. What's the major source of calories when he is consuming this comfort food? So this is a quick one, so just put in an answer. All right, that's good. That's quick. There's only 3 options. All right, a few more seconds. All right, let's see. Okay, nobody went for protein. That's good. It's either fat or carbohydrate. Which one is it? You can actually look up the calories, you know. So I picked something similar to what he's got there. And if you check it out, there's 8 grams of fat, but 25 grams of carbohydrates. And a lot of that is simple sugars. And if you remember the little math thing that I told you, that sort of generalization, that fat is worth about 9 calories per gram, that works out to 72, but carbohydrates are worth about 4 calories per gram. So that's 100. So carbohydrates is actually the main source of, and there's a little bit of protein, but carbohydrates are the main source of energy or calories in the ice cream. And you'll notice here that this is for 1 serving, which they say is half a cup. And I don't know if you know how big half a cup is, but under these circumstances, there's no way that Saurabh is stopping at half a cup. So if he eats the whole thing, then it might be this much. But anyway, the point is he's taking in both, it turns out, fat and carbohydrates. So now we can think about the impact that that's going to have on his energy metabolism as he's lamenting what he's just seen. So now just to briefly talk about regulation of insulin glucagon, under high glucose conditions, which is what you're going to have when you are consuming this ice cream, insulin is going to be in your bloodstream. And so how's that going to affect these processes? Well, that, as I talked about before in the earlier clicker question, that is going to inhibit lipase. So we're going to stop breaking down triglycerols because we have a lot of glucose. And it's going to do the opposite. It's actually going to activate the synthetic pathway to synthesize fatty acids from acetyl-CoA. And as he's breaking down glucose, he's going to make some acetyl-CoA, and that is going to then be converted to fatty acids. And likewise, he's going to be intaking a lot of fatty acids, and that is going to be taken up by the adipocytes and stored as triglycerol. And these ketone bodies, well, that pathway is not going to happen at all because you only make ketone bodies under low glucose conditions, right? So the liver is not going to use the acetyl-CoA for ketone bodies. It's going to use it. Yeah, it's going to use some for its own needs, but it's also going to store a lot of it as fatty acids. So basically, we're converting the glucose to fatty acids and storing that. So this is sort of, if you're trying not to put on weight, the ice cream is maybe not the best thing to be overindulging on. And this is actually the basis, right, of the Atkins diet, the so-called low carbohydrate diets, right? And Atkins, and I'm not necessarily endorsing this diet, I'm just explaining the biochemistry behind it. If you don't eat carbohydrates, your blood glucose tends not to get that elevated. And so you tend not to promote the storage of fatty acids as much as you would if you were consuming carbohydrates along with fatty acids, right? And so that's the basis, that's the logic behind that diet. Again, I'm not endorsing or any diet or anything. I'm just explaining it, okay? And then conversely, if we think about a low glucose condition, glucagon is going to be present in the bloodstream. You're going to turn on lipase, which is going to break down triglycerols and fatty acids. Those get released into the bloodstream. And we're going to just basically push everything all the way through. And under those conditions, you're going to take make ketone bodies, and the brain is going to use those, okay, from the fatty acids, okay. So that, but that, and that was quickly through the regulation. But by now, those thought processes should be familiar to you, right? It's the same basic message I've been giving the whole time. And that takes us to the end of topic 12. We talked about what happens when blood glucose is low. And we make ketone bodies when that happens. And then when it's high, we store fatty acids. And I'll tell you what happened to SORAB next time.